of Bengal. But being a coastal city, the elevation difference is very less. And if we dredge it, then most probably we'll hit the water level of the Bay of Bengal. So nothing will go out. And we cannot widen the river, because then it's a matter of politics, because all the settlements are there. But still some kinds of clearance is going on nowadays, but it's not a very good option. Now, on the other hand, locally, these small lakes or natural depressions are called tanks in South India. So there are 163 tanks. These are, we have digitized from our LiDAR's data. This is like 1 meter resolution data. So from that, we could find out 163. They have considerable amount of storage. Okay, so we were thinking, let's say if we can connect them or if we can dredge them, then whether we can solve this flooding problem a little bit. Means if we can store the rainwater before it comes into the river and then flow through the city, then I think we can reduce the magnitude of the flood. So in that direction, the Water Resources Department of Tamil Nadu, they proposed 1 to 2 meter of dredging for many lakes with the cost of $16.5 million. This has not been implemented, it was proposed. But we did not find any scientific study on what basis this decision was taken. Then we thought that it's the time we should carry out the scientific work. So for this, the first and foremost step towards flood protection will be to simulate the flood accurately. And so this will help in ascertaining the flood hazard zones in issuing warnings. So for that, we need a flood simulation model, and we need to set it up for the basin for evaluating flood scenarios for better management. So if we want to manage, then we should go for different scenarios, and then we have to come up with a good decision. So for scenarios for the future, such as we have to consider many things like urbanization will go on. So what will be the effect of urbanization? Then because of climate change and many other factors, rainfall pattern is changing. So what is the projected rainfall? And there is growing means thing like sea level rise, because Bay of Bengal is there. During tide and low tide, those who are living in coastal city, they know this thing. When there is a flood, and at the same time, if there is a high tide, then this is the worst condition, because water from the river will be blocked by the ocean water. It cannot go out. So sea level rise has severe implication. And then in the case of Chennai, we have different kind of tank management scenarios, like influence of preservation, because this aspect has been considered with the view that many lakes are getting encroached. So if we preserve them and if we defend them, then how it will behave with respect to urbanization and climate change. So these are the options. Now, if we want to integrate all these things, and if we want to use some model, then we need a very systematic framework. So in this study, we have limited it to three modeling aspects. One is urbanization modeling, then hydrological modeling, and then hydraulic modeling. So for this is the area, and this is the Chennai city area. Okay, so first what we do is we'll use this hydrological model, and for the hydrologic model we need elevation, soil data, land use, land cover map. That will go as input to the hydrologic model, and this hydrologic model is used for the entire basin. And then we'll get the runoff or flood hydrograph at the inlet here in the hydraulic domain. So this entire area is hydrologic domain, and this shaded area, this part, this is called hydraulic domain. So at the inlet of hydraulic domain here in the river, we will try to find out what is the hydrograph. Okay. So if we get this flood hydrograph from the hydrologic model, then this will be input to the hydraulic model, because from the hydraulic model we can get inundation extent or flood map. So once we get this hydrograph, then we run the second model, hydraulic model, and we get the inundation map. Now in the hydraulic model, we have, this is the upstream boundary condition, and in the downstream side we have tide condition, because the river mouth is open to the Bay of Bengal. Now when we are running this hydrologic model, we are considering different conditions like precipitation change. We are getting a different scenario. Now we are giving urban sprawl prediction. That means, let's say we have the present urban condition and what could be the future condition. So let's say if we consider the entire area, then we can consider it like pixels, like one large photo and we have small pixels. Now in each pixel there will be change, whether it will be urbanized or it will not be urbanized. Okay, if it is urbanized, then the features will change. Once the feature change, then the runoff pattern will change. That is the idea. So we predict the LULC map, that means urban sprawl, for in the future scenario, and we use it in the DEM model, LULC, DEM, everything, and then we get the response from the hydrologic model as flood hydrograph. Okay, so whatever changes are happening in the hydrological domain, that will be reflected at the flood hydrograph, in the flood hydrograph at the inlet of the hydraulic model. So we are changing rainfall pattern, we are changing urbanization, we are changing the water sprayed area of the lake. That means we will be deepening the lakes and storage capacity will change. And then some of the lakes which are not very big, they may disappear also in future if this kind of encroachment goes on. So we have considered different scenarios and we have run the hydrological model again and again, considering all these things, and we have generated this hydrograph, flood hydrograph, and then for each scenario we have run the hydraulic model in the hydraulic domain, and we have got the inundation map. Once we get the inundation map, then we can go for flood hazard analysis. Okay, and then we can analyze how the storage capacity in the lakes or tanks is helping in moderating the floods in the Chennai city. So this is the overall methodology. Now let's go to the next section. So if we summarize all these things, then we have three objectives in this study. First one is modeling possible future urbanization scenarios for the basin. So for this, we need one urban sprawl prediction model. Then we have to set up hydraulic model for simulating the inundation map. Then in the third objective, we are trying to investigate the role of preservation and deepening of the tanks in fluvial flood characteristics. Please note that when we talk about urban floods, we have two things, fluvial and pluvial. In case of fluvial flood, it is because of overflow from the river. In case of pluvial flood, it is in addition to overflow, the contribution of drainage network system, because they will also interact. If you look at the Mumbai flood, then the drainage system also contribute. Means water from somewhere else, it will come, and from the manhole or from the opening, the water will be discharged on the streets or somewhere, and that area will be flooded. So that is called pluvial flood. But we are focusing mainly on pluvial flood. We are not considering drainage system. So let's say how to address the objective 1, that is modeling possible future urbanization scenarios for the basin. Now for this, we have some standard models available in the public domain, and one very good model is Sleuth. Someone was asking me about urban sprawl prediction model. So this model is very good and it is well tested. So we have used this model for urban sprawl for the Chennai city. So the inputs are different. Like we have to supply LULC maps for the past, let's say decades, few decades or some intervals, and then the model will run. You have to give different conditions, and then it will try to predict the future LULC map, like 2050. Okay, so if you see, it's getting highly urbanized. We have developed another model because the sleuth model is very intensive. So we were thinking, why not to develop one simplified model? So we developed one ANN model. So in the ANN model, we gave several inputs. These inputs are influencing factors for urbanization of a city. Okay, these are based on from different literature, and we have come up with respect to Chennai city. And it has 3 layers, and it can also predict the urban sprawl, and we have got it for 2030. So if you look at this sleuth output and this one, there is not much difference. So we have overlaid here. Here in the left side figure, we have ANN on the top and sleuth in the bottom. And you can see that some differences are there. Same thing if you look at sleuth here and ANN here, then also there are some differences. So what happens? This means that whenever you use some urban sprawl models, there will be some differences. It may not be significant, but it is worth to find out the sensitivity of the models. Means if your final target is like flood inundation, what could be the differences or in the accuracy level, or you can estimate the uncertainty of the urban sprawl prediction. So if you use a different model, you consider the effect in the inundation map. Okay, so we have used these 2 models. Now the overall methodology for urbanization is, so as I was telling you, you have to give LULC maps for the past few years, and then this can be used, processed in the model to predict urbanization. Now, this validation means one set of data, a few set of data. It will internally used for validation, and you can estimate what could be the R square for the, let's say, it is 2021. Maybe you can use 2020 actual LULC map of the city for the RDR basin, and what is the predicted city, and pixel by pixel it will compare and give you some accuracy idea. Okay, so these changes in the pixels should be reflected in the hydrological model. So once this part is done, this urban sprawl part is done, then we go to the hydraulic modeling framework, and then we can investigate what is the error that is propagating from different types of urbanization model. Okay, so let's say once this urban sprawl prediction is done, then we can go for setting up of hydraulic modeling framework. Okay, so let us focus here now the hydraulic modeling framework. So historical and predicted land use maps are there. So historical means here we have tried to simulate 2 actual flood events, 2005 and 2015. So for that we have the LULC map for those years. So those are like historical. and some predicted means for future 2030, 2050. And then upstream boundary conditions for various tank management scenarios. We will be putting this condition and then we'll run the hydrologic model to obtain the flood hydrograph. Once we get that thing, we'll run the hydraulic model, and then from the hydraulic model output, we can look at peak flow, inundation extent, and we can classify flood hazard zones. And then from here, we can analyze impact of disappearance and deepening of the tanks. So now let us talk about the hydrologic model. There are different hydrologic model, but here we have used HMS. In general, means my research group, what we do is we try to avoid using any commercial software for research purpose. The idea is very simple. When our students will graduate from here, we don't know where they will go. Some of them, of course, will go to very big institutes. They will get all the facilities, but some may not get that kind of facility at the initial years. So buying the commercial softwares can be a big issue to carry out research. So this is my idea. I ask them to use freely available models, tools, so that they can continue research without any problem. Not only that, my group is developing different kinds of models, so they know how to develop model, how to use them. So there is no issue like for funding, we cannot do the research work. So here HMS, it is a freely downloadable model. This is a hydrologic model. Okay, so here different steps are there. So for loss, we have used SCS curve number. Then for transform, we have used lag time approach. And the routing, there are many options, but we have used kinematic web, that option. Now, in the HMS model, some components are there, major components. One is input data components, where we have to give the model input like time series of data, graded data, parameter, boundary conditions, all these things. Then one model is meteorological model. So we have to supply all the atmospheric conditions like precipitation data. Then before we run the basin model, we have to give control specification like time period, time step of simulation, etc. Then the basin model will run, and finally we will get rainfall runoff response. That means we can get the flood hydrograph. Now this we can get at different locations wherever you want. So in our case, we have recorded this output at the inlet of the Adair River to the hydraulic domain. Now when we use HMS model, we need to calibrate it because and the problem in India is we may not get all the data. So again, we rely on many open source data, but then calibration becomes a little bit difficult. So there are different steps for calibration. Whatever rainfall data you can collect, we could collect some rainfall data from one is there like Minambakkam, one rain gauge station is there. We got the data from there. Then here we estimate then simulate the runoff, and if there is any discrepancy in the runoff, I'll come to this point how we have calibrated. That means at some point, if you have the measured data for a particular rainfall event, you can compare. If you are happy, then you can stop. If you are not happy, you have to calibrate some parameters. Again, go here, again run it till you get your desired accuracy. Okay, then you can stop. So let's say HMS model is done. Then we can go to the hydraulic model. Now again in the hydraulic model, we have used HCRAS 2D model. The previous version we have used HCRAS 5. Now HCRAS 6 is released, and HCRAS 6 is having another new addition, that is sediment transport model. So those who are interested in sediment transport modeling, they can download the newer version and they can practice it. So the HECRAS model, we solve mass conservation and momentum conservation, whatever I was discussing in the forenoon session. Then we have grid discretization. Now in HECRAS, there is one fantastic idea that is called subgrid bathymetry. Okay, so I'll discuss this aspect in detail, how we can take care of buildings with the help of subgrid concept. Okay, and the solution method is finite volume. And the required data sets are topography, maps, LiDAR data. It depends whether LiDAR data is available or not. Then some historical information, and you need some experience to run the model. Okay, and then you can use it for different purposes. Okay, I hope all of you know some resources, freely resources. I was talking about SRTM data. That SRTM DEM data is freely available with the accuracy 30 meter. But don't use it blindly here and there. You have to use it judiciously. But this is a good resource. Or topography. Now, in the HECRAS, there are many options. Like you can use it in 1D mode, but if you look at the river, it's going like this. Too many bends are there. So 1D may not be a good option. Then you can go for full 2D approach, or you can go with 1D 2D coupled approach. That means sometimes what happens if it is 2D model, let's say, especially you can use coupled 1D 2D model for a situation like, let's say the river is coming like this and it's flowing like this, and here there is urban settlement. But for certain stretch like this, there is no urban settlements. But if you represent this area with 2D model, then it will take unnecessarily extra computation time. So maybe from here to here, you can take 1D, then this portion you can take 2D, and it will automatically couple here. So you can save computation time. And you can get almost similar level of accuracy. So this is why I have highlighted this thing here. This approach is there in HECRAS. So for 1D river, we need cross-section data at certain intervals. Here I have highlighted some points like this. Now, this survey you have to conduct in such a way that the bends are captured properly. Okay, and somewhere where the cross-section is changing very rapidly, we should take the cross-section data. But in general, there is no like standard that at what interval we should take. It is like based on your affordability, how much money you can invest. But still, for scientific purpose, we need some level of accuracy when we are conducting this kind of survey. So if it is coupled 1D 2D, then this will be the river part will be 1D and this part will be 2D. Again, in the 2D domain, if you have some important features, like let's say here, this part, if there is a drain, the drain dimension will be small. So you can use some refined grids. This option is also available in HECRAS. So if you choose to use coupled 1D 2D, simple 2D, in coupled 1D 2D, 2D is there. Okay, so that's why I'm not only focusing 2D, I'm trying to give you the idea of 1D as well, so that you can understand, means what are the options. We have the option like 1D, 2D, coupled 1D 2D. Now how to couple this 1D 2D? They have two options. One is frontal coupling. That means 1D river is going and then one 2D domain is there. This is called frontal coupling at the front. Now 1D river is flowing through and on either side you have floodplain. Then on either side you have 2D. So this is called lateral coupling. From left bank to left floodplain, right bank to right floodplain. Okay. Now how to do this algorithm, means how to solve it. Of course, this idea is already there in the model. So one is direct river to tutti flood area. So in this type of connection, let's say if you have a river like this and you have the cross section data like this, so this and this will be connected to the floodplain. Okay, and the 1D river passes through the flow to the 2D flow area, and then it will pass the flow like this at one section. Okay, then another option is lateral structure. So as if between this and this cross section there is a lateral structure like weir structure or something, and the flow is overflowing over the weir structure, and in this area you have the 2D flood domain. Okay, if you go through the technical manual and the user manual, you'll understand it. Okay, now if you look at this river, this Chennai area, then it is like a highly urbanized city. So we were trying to figure out how to represent the building. So for that, we need very high resolution DEM, and you need the building layouts. Now, how to get the building layouts? It's a difficult situation, but there is open source. I'm writing it here. Maybe you can note down. We call it OpenStreetMap. You can get the building layouts for many cities. So in this case, we downloaded that layout, and in GIS, we fused it with our DEM, and then we could mark out the building layouts, and then we treated the buildings. Okay, but for this presentation, I have focused here in this part to show you the effect of buildings. Okay, this is called Aripuram area. Now, how to represent the buildings? Different models, they have different algorithms to represent the buildings. Okay, in HECRAS you can adapt many other strategies, but we have done the simplest one. But if you use Mike or some other model, then maybe you can implement one of these methods I'm going to discuss. First one is building block. That is one approach. Okay, so in this method, you generate the grid for entire domain, and then you have the building layout. Then around the boundary of the building, whatever cell edges are there, you raise them to the roof height. So let's say this is one building, this is building area. Okay, so this outside line, you give the elevation, means inside this domain, you give very high elevation. Then automatically water cannot flow in this side, right? As if there is a wall. So this is one kind of approach. This is called building block approach. Now, the next option is building hole approach. Building hole approach means what they do is we have the layout of the buildings. There will be no grids within the building like here. Okay. So in this case, you need very high skill to develop the grids. Okay. This method is very much available in Mike software. Okay. Now next one is building porosity. This is like approximately representing the buildings. So instead of representing the building in the domain, we represent the effect of the building on the flow. So for that, there will be building drag coefficient, some other distributed parameters. So here we need special model for this. So there is no exact representation of the structure geometry. So we just get the effect. And then there is building resistance. This is another approach. If you look at the momentum equation, on the right hand side you have the source term, like a bed slope term and friction term. Now, in the friction term, if we increase the Manning's value too much, then in the left side we have dou qx dou t, let's say x momentum equation. Dou qx dou t, then we have the flux term, then we have the source term. Now, if we increase the Manning's value too much, then dou qx dou t will almost be close to 0. So we'll get velocity 0.
So we are not able to see the slide, the one which you're speaking right now.
Oh, just a moment. So slides are there or not now?
It is there, but not moving.
Okay, just a moment.
It was not moving. I mean, you were explaining the formula equation, but that was not being seen.
Now can you see building resistance?
Yeah, building resistance.
Yeah. So right side, maybe these pictures are a little bit, Miss memory is taking more memory, so it's not coming. So now it is visible, right? Okay. So
I mean, the same building resistance is visible.
31st slide is going on. 31st.
Yeah, 31st. Yeah.
Yeah.
Right side, can you see the?
Yeah. Right side is visible.
Yeah, there is a picture here with triangular grids. Can you see it?
Yes.
Okay. Yeah. So in this method, we just increase the Manning's n values for the cells covering the buildings. Okay. So indirectly we'll get the effect. But we have taken a different approach. Now I'm on slide 32. So here in HECRAS, they have one concept that is called subgrid concept. Now, what is this subgrid concept? HECRAS will use two different types of grids. This one is called numerical grid, and this is called topography. So let's say for the Chennai city, I have a high resolution DM. And let us consider 10 meter. Beyond that means we need a very highly efficient computer. So we have 10 meter resolution grid. That DM we have. But we can go for finer because we have 1 meter resolution grid. So we operated on 2 meter resolution. So let's say we have 2 meter resolution grid. So that will represent the topography. Now, if your cell size is 2 meter by 2 meter, then you have to solve like 20 lakhs or 30 lakhs computational cells. Means it will take too much time. It will really means for one flood event it will take 3-4 days. So then the whole purpose is defeated. So what they do is they represent this topography in this way, but the numerical grid where the fluxes are calculated, that is bigger one. So let's say 1, 2, 3, 4, 4 by 4, 16 cells, they will define the topography, but this one grid will define the numerical grid. So fluxes, actual numerical operation will go on here. Okay. So if it is only coarse grid, then we can see it like this. But if you are using subgrid, then we can see the variation within the numerical grid. So you can capture the small variation in the topography. So how to take care of the buildings then? We need high resolution DM. By the way, this is approximate. It's not like building whole or building block method. It is in between somewhere. Okay. So this is high resolution DM is required. Then we need the building layouts and we have to fuse it with the DM. Then now buildings can now be raised by a certain height. Okay, in this cell, wherever there are buildings, if there is a layout, let's say here, then these cells should be highly, means you have to increase the height. Okay. So in this way, you can indirectly block this area and you can represent the buildings in HECRAS. So this subgrid concept should be used for numerical computation. So this is a very good approach, means you can still capture the details of topography. Now with this we have simulated the hydraulic domain. Now we are coming to investigating the role of preservation and deepening of the tanks. Okay. So there are almost 163 water bodies. We have identified them, and then now we are solving it for different scenarios. So we have historical floods like 2005 and 2015, that is H05, H15. Okay, then we have urban sprawl. So let's say by 2050, what could be the urban expansion? And then rainfall is like similar to 2005 and 2015. That means by 2050, we are considering the urban expansion, what is the features, and we are generating scenario for similar rainfall like 2015 and 2015. Now for the tanks, TP means tanks in the present situation. It's whatever bottom levels we have. We have taken one uncertainty during the flood event. We don't know how much of the tanks will be filled because we don't have that much data. So we have considered 50% filled and 75% filled. So generally what happens during the flood season, for 1 day or 2 days there will be less rainfall. By that time water will come and it will be stored in many lakes, and then if there is intense rainfall, no water will be stored there almost, then everything will flow as runoff. So we have taken in this way these two scenarios. So now in the future scenario, what we are doing is we are considering this for this two scenario. Now the tanks as if they are dredged 1 meter and 2 meter, two different options. So we are doing it like uniformly. This is just a scenario. So all the tanks are deepened by 1 meter. All the tanks are deepened by 2 meter. And another scenario, TD means tanks disappeared. All the small tanks, they are not just there. Then what will be the scenario? Now, model calibration part, hydrologic model. For hydrologic model, for the first years, we don't have any that kind of observed data. Only data we have like in case of this Chambermakkam Lake, there is at the upstream side, there is some major data, inflow data. Otherwise, we don't have any major data. So we have tried to compare the inflow volume to the Chambermakkam Lake, and we have got quite close data. This is for 75% full, and this is also for 75% full. Or I think one is for 2005 and another one is for 2015. I have to check here or something. We have considered this thing. Okay, so this is like at least we can say that the hydrological model setup is quite okay because we don't have any other major data. Then for the hydraulic part, for 2005 flood, we don't have any major data. And we don't have any satellite image also because of cloud weather. And for 2015, we don't have any good satellite image data for inundation map because it was thickly clouded. We can see some map, but they are not so realistic. But soon after the flood, then ISRO, this NRSC, ISC Bangalore, Chennai, and many organizations, they came forward and then they collected the flood mark data at different locations close to the Adyar River. So we have tried to validate our model output with that data, and the comparison is R square equal to 0.8, which is quite okay, quite good. So in this way, so we have validated 2015 hydraulic model data And with same model we have used for 2005, we are assuming that because other than the calibration parameter, nothing is changing. If you run the hydrologic model for 2005 like flood scenario and with a different upstream conditions, okay, like a tank in the present condition, tank with 1 meter dredging, tank with 2 meter dredging, then this is the discharge pattern. And this is for 2005 like flood scenario. And this is for 50% initial full, all the lakes, and this is for 75% full at the initial condition. So we are getting this type of flood hydrogram. If it is 2015, you look here, there is a difference. When it is 2005 flood, there are effects of dredging. But when it is 2015, there is not much effect. Now, the reason is very simple. Because 2015 flood was so severe, the lakes, all the tanks, they got filled very quick. Okay, so they were not playing any role. After that, means everywhere water. But in case of 2005, it was a moderate flood, so it's doing some job. Means it can play some role in reducing the flood peak. So this is the inundation map for 2005 flood-like scenarios, and this is for 2015 flood-like scenario. Okay, now some observations for 2005 rainfall event, which is like 1 in 50 year. So disappearance of tanks causes the area of inundation to increase from 18.6 square kilometer to 28 square kilometer. Okay, for the urban sprawl of 2050. That means inundation is increasing if there is urban sprawl when there is 2005 kind of rainfall. And the initial fulfill 50% or 75% initial condition in the tanks. Now, depending the tanks by 2 meter, this is a very good information. Means if we depend the tank by 2 meter, then it can nullify the increase in inundation area due to urbanization. That means, let's say in 2050, we have the urban sprawl. We have similar rainfall like 2005, but all the tanks are dredged by 2 meter. Then we are getting similar inundation extent like 2005 flood event. That means if we depend all the tanks by 2 meter, we can nullify the effect of urbanization by 2050. However, if it is 2015 like rainfall, then the disappearance of tanks for that condition, what will happen? The 1 in 50 year rainfall, whatever flood inundation we are getting, that will reflect as like 1 in 100 year rainfall. So if the tanks disappear, 1 in 50 year and flood for 1 in 50 year rainfall event will appear or behave like 1 in 100 year rainfall. That means 2005 flood will behave like 2015 flood. But if we even depend for such a huge rainfall, there is no difference. That means the storage in the lakes are not playing role when the rainfall is huge like 2015. And then we did some like hazard analysis. So we have classified based on the depth of inundation, low, moderate, high, very high. And this I think we took some British standard, and we have done this analysis. This is like simple Excel calculation. And then I think this slide I have repeated. Yeah. So these were the two major conclusions here. How the flood management tanks are playing a role in flood management. And I would like to stress one more thing. If we don't consider this subgrid concept, then this drainage, and those who know the Chennai area, they know the Buckingham Canal. So we were not getting these things at all if we don't use subgrid concept. So now, this side we have punched the buildings. In the left side, there are no buildings. So this will affect the entire flow pattern and the depth also. So I'm trying to play this animation. Hopefully you'll be able to see it. So when there is no building in the domain, it will flow like this. This is from HECRA's output. So I must appreciate my PhD student. She's like artist. She has added some water flow sound in the background. And this is when we have the buildings. Look, now we are getting better flow dynamics. So if you look at this area, this Aripuram area, and then this is the maximum flood inundation extent for 2015 flood event. So before I conclude, I must thank my PhD students, especially Nitila Devi, and she has published 2 good works on this topic, one in Journal of Hydrology and one in Water. And then I'd like to thank my student, he'll be graduating soon, Sridharan, and he has published 2 papers considering this Chennai flood, one in water resources research and one in advances in water resources. And then I'd like to thank Reshma. She's doing mostly experimental work on urban flood, and she will be doing some numerical analysis also. And I would like to thank my colleagues, Professor Balaji Narasimha, who has supported me for giving different kinds of data and hydrological model setup. And I'd like to thank my colleague, Professor B.S. Murthy, who has helped me for this hydraulic simulation part also. So that's all. Thank you. If you have questions, doubts, or any queries, you can ask me.
Any queries, please? Maybe directly you can inquire, or otherwise you can put it on chat box also. Okay, all of you can unmute and you can speak, please. Those who want to have queries, please unmute yourself. Please unmute yourself and then speak, please. Yes, please. Any queries, please? Please unmute yourself.
They understood very nicely, so they may not have any questions.
Yeah.
Hello, sir.
Yeah.
Yeah.
Am I audible?
Yeah.
Yes.
Yes, please, Shatrugna Singh ji.
Yeah. Thank you, sir. It was really a nice lecture and a simple one to understand. I have actually a question from management point of view.
Yeah.
That if we can somehow, if we can show to the policymakers and to the stakeholders that this is what the scenario is going to be in next 50 years or 30 years. Why cannot we discourage people building houses in the flood zone areas? Or how we can achieve that kind of objective in society?
Yes, sir. We three, like Professor Balaji Narasimhan, B.S. Murthy, and I are involved in the flood forecasting system for Chennai city. One company is developing and we are monitoring. And this study, what we have published, it came in Water Network News also. So there is some kind of sensation, but maybe through our this flood forecasting system, we'll try to reach out to the policymakers. This we have realized, but this is a not so easy task. But of course, we'll put our votes and then let them decide.
Yes, sir, because we have been observing all over the India the same things happening, whether we go to Haridwar, Rishikesh, or if we go south, or if we go to east, or if we go to west, anywhere we go, this is now getting very common phenomena that urbanization is taking place in the flood zones of the water bodies, and the government and the people who are responsible to implement the government regulations probably somehow it's bypassing them, and the people are constructing there, and then when something like this catastrophic happens, then we held government responsible, but that's where we do not realize that it's not government's. I mean, why I am all saying is this, because I have experience of staying abroad for 10-12 years, and I have realized like there they have regulations, especially in terms of insurance, that everyone has to have a mandatory insurance for house. So if you have to have a house insurance, and if you are building your house in a flood zone area or in a catastrophic prone area, you will pay high insurance, high premium. So if you have to pay high premium, then obviously you will avoid paying high premium, and you will stay away from the flood zone. But in India, because we do not have such kind of rules and regulations, we cannot enforce people, but rather we have to kind of do outreach activity to educate them that this is not going to be kind of helpful to you in the long run. um, I don't know, I mean, it's a kind of a gray area where the policymakers and the stakeholders should be more proactive.
Yeah, yes. Recently, actually, there was a hearing from Madras High Court. Those who knows this OMR means there is a like a IT corridor. Huge lake was there, and it has been enclosed like anything. Then one NGO has registered a case, and we were assigned the task means what is the fallout. And few days back, in all the newspapers that came out, as if we are responsible because we told them that it has been encroached.
Right.
Yeah.
Yeah, I raised this issue also because I have worked almost 1 year in Hyderabad, and Hyderabad is also another city which is known for lakes, which used to be known for lakes. They had more than 1,600 lakes, but now roughly 400 lakes are left, and you never know what will happen in next 30, 40, 50 years, whether there will be any lakes or not in Hyderabad. So, and whatever lakes are left, actually, they are basically the dump yards, not anymore lakes. They are basically the dump yards for people living around those lakes. So it's sad that how unsensitive we are becoming towards our ecosystem, towards our environment, um, as we were like 30, 40 years back. Um, I don't know. I am loss of words now. It's sad to know about all this.
Yeah, any other queries, please?
Yeah, sir, one question regarding the modeling of the urban sprawl. Sir, what about the validation of the sprawl? Like if it begins in 2002 or 5, in between, is that intermediate sprawl has been used as a validation or no?
Yeah. Means in the model, especially sleuth model, in between we are giving. I think I don't remember exactly 4 or 5 cost maps. Then one map they are using it as validation purpose. So pixel by pixel. They are predicting that map, and the original map is there, and then pixel by pixel it will be compared, and they are giving some kind of accuracy level and how much means it can predict. That is there.
So is in that no ANN works better, or sleuth is giving a better result?
Sleuth is a little better than ANN because sleuth has more features, and this ANN model we have developed as a simplified version. We have not considered too many things, but this accuracy is also not too bad.
Okay. Okay, sir. Thank you.
Thank you.
Any others, please? Yeah, you can just put it in chat box also. If any connectivity issues are there. Any other issues, please? Okay, Dr. Kuiry, thanks.
Yes.
And namaste.
Thank you. Thank you.
And
Sir, sir, one more. I mean, for urban sprawl, sir, what was the resolution of the data? If you can share, no, to get, was it freely available data, or it was?
Landsat data. Landsat data was used.
Okay, Landsat was used. Okay, fine. Thanks.
okay, then we shall end today's thing with by saying Dr. Kuiry, thanks for all the way delivering, particularly online. It is sometimes, nowadays it's okay, but we never used to deliver lecture for such a longer time, particularly virtually. And there is a lot of difficulties, technical difficulties, etc. But yeah, it's also an experience. We also learnt a lot, and thanks for your very nice presentation, particularly for the research scholars. We are given so much of wide scope for next researchers, and also since you are working on a Chennai floods, is a very fruitful and useful thing also in future. So thanks once again from on behalf of the university and also on behalf of the ATAL Academy of AICTE and also on behalf of all the participants. We thank you, Dr. Kuiry. Thanks very much. It is just maybe this is the first direct interaction. We want to have it from you. We like to invite you to Pantnagar whenever we are permitted. Okay?
Yes.
Thank you.
Thank you. Thank you.
Thank you. Thank you. Please.
Thank you all.
And if you want to give any material, you can just pass it on to me. I will just put it in their mail or like that.
Okay. Okay.
Any maybe published papers, related papers, or maybe I don't know that you need to say.
Okay.
If you are comfortable and you can pass it on to us,
Yes.
so we'll distribute the material.
Yeah.
That's the request.
In fact, I will encourage participants because sometimes immediately they may not have questions. If you have any questions or queries, you can write email to me. And, I'll be happy to share even our research ideas and all the publications. So it will not be a problem.
Yeah. Thank you, please. Thank you. Thank you, sir.
Thank you.
Okay. Namaste. Please, participants, you please stay for a while.